All right, the derivation we're going to be looking at today is for the simple pendulum. I've exaggerated the picture, but basically we would have a bob mass hanging on the end of a massless string. Here I've labeled the length of the string as L, but it's important to remember that this is also the radius of some circle that this bob mass would swing if it were allowed to swing all the way around. We're going to measure this distance from here back to the equilibrium position as x, and we're going to define the weight of the bob mass as f of g pointing down. Given this initial setup, we can label that the tension, f of t, is along this direction back towards the center, which would be a centripetal force. And then this f of g can be broken apart into one component this direction and a perpendicular component this direction, where this side would be mg cosine theta and this side would be mg sine theta, excuse me, based on f of g being mg and, of course, this angle being theta in comparison to the similar triangle up here. Now, something that we are doing that is a little bit special in this particular derivation is we are assuming that the angle theta is less than 15 degrees. This allows us to take a shortcut mentioned in your book for angles less than 15 degrees. We can say that the sine of theta is equal to just theta. And so in the particular derivation that we're doing here, if we think about mg sine theta right here, this force is pointing back towards the equilibrium position. The mg cosine theta is simply what's generating the tension. And so if you think about what is causing the pendulum to swing, it's true it is f of g, but it is not all of the weight that is causing this object to swing, because some of the weight is simply generating the tension preventing it from falling. And you can imagine that that would be absolutely true if the pendulum were stationary here at the equilibrium position. So this component, mg sine theta, is what we would call the restoring force. This is analogous to the restoring force for springs. If you remember Hooke's law as Fs equals negative kx, the pendulum has a restoring force that is a component of gravity pointing back towards the equilibrium position. And so we say the restoring force is mg sine theta. Now ultimately this would be this would include a negative sign, although since this is symmetrical from side to side, it's not of utmost importance to worry about the sign at this point. But what we are going to do is employ this assumption in order to simplify this to just mg theta. So with theta less than 15 degrees, the restoring force is simply mg theta. And so if we think about our radial or rotational terms, theta is a measurement in radians, effectively, of this triangle up here with the simplified sine theta function. If you think about the simplified triangle that we have going on here, then theta can be re-evaluated or redefined in terms of the sides of those triangles. And so what we have is theta equals x over L, and so if we substitute that into here, then our force becomes mgx over L. And so if we rearrange this just a little bit to put the mg over L in the first term, mg divided by L times x. This is similar, but not exactly the same, to Hooke's law, f of s equals negative kx, right? Keep in mind that I said there should be a negative sign ultimately here, which is what makes this really look like that same formula. And so that means that mg over L in this particular system, which is a pendulum, which doesn't actually have elasticity, right, mind you. It just has the force of weight as a function of its length, giving it a restoring value that pulls back towards the opposite direction. You can imagine that this is, if I think of it like this, then that means for pendulums, we can let K equal mg over L. And so why that is ultimately so important is that we have a formula for the period of a oscillating system from our simple harmonic motion unit. We have a formula T equals 2 pi square root m over K. And so if we let K equal mg over L, we can substitute in that value for K in this formula. And what that does is that gives us, here I'll write it next to it, T equal to 2 pi times the square root of m divided by mg divided by L. And so we have m's cancel and the g and L terms will inverse. And so we end up with a period, T, equal to 2 pi times the square root of L over G. Now, why is that significant? Well, given the assumption that we made at the top that angles less than 15 degrees, which is really the only thing that we've done to make this kind of work out exactly as it has, but given that one assumption, for angles less than 15 degrees, 2 pi times the square root of L over G defines the period of a pendulum as a function of its length and gravity, and most notably, not a function of its mass nor its amplitude. Now, this is true that for assuming less than 15 degrees, the amplitude should be less than 15 degrees, but what you'll find is in experimentation, even at angles above 15 degrees, this is a great approximation. And so what ultimately is the takeaway is that m, mass, and amplitude A are independent of period.